Let's look a little bit at the intraseasonal variability in the oceans. You would expect that when we say coupling, air-sea coupling, ocean-atmosphere coupling matters for MJOs and MESOs, you expect that oceans also have intraseasonal variability. And the most fundamental question then is whether ocean intraseasonal variability is mostly forced from the signals we see in the atmosphere. When we say they are coupled, what does it exactly mean? Can the ocean generate its own intraseasonal variability, and does that then influence the atmosphere, or is it always that the internal variability in the atmosphere is being coupled and then they become coupled intraseasonal variabilities? Why do we ask that question? Basically, ocean is much heavier than the atmosphere, moves much slower than the atmosphere, so the 1,000 times heavier density and higher heat capacity, etc., must mean something. Without going into details, I'll just mention that there are regions in the ocean where the forcing from the atmosphere, ocean is obviously forced from the atmosphere, other than the small forcing below from geothermal heating and so on. So the wind forcing and the heating and cooling, if we stay in the deep tropics or not go into polar latitudes where you have density driven circulation, so you have this forcing that's being imposed on the ocean, and even the low frequency forcing that is beyond the intraseasonal timescale can generate barotropic and baroclinic instabilities in the ocean, so horizontal shear and vertical shear in a simple sense, and that can be available potential energy when that instability of barotropic and baroclinic structures crosses a threshold. The available potential energy can get translated into kinetic energy, and then it's a matter of scale selection. Can that kind of instantaneous instability generating kinetic energy be in the intraseasonal time scale? Okay, those are kind of the fundamental questions. But the ocean structure matters as well. This is what Billy Kessler's chapter in the Lau and Walliser book focuses a little bit on. What is shown here is the so-called barrier layer structure. So think of the typical ocean near the surface. Because of the heating, cooling, mostly from the wind forcing, there is turbulent kinetic energy generated, which creates a well mixed layer in the ocean. So you can see here the salinity structure and the temperature structure. They're well mixed down to some depths, and then you have sharp gradients, the halocline and the thermocline. If you look at the density, you get the pycnocline, and that's what we would typically call the mixed layer, the ocean surface mixed layer, where you have this kind of structure. But the surface forcing can then add things like precipitation, in which case the wind burst that's typically associated with the convective phase of precipitation, let's say the MJOs or MESOs, can create a freshwater lens, which can then generate a halocline or a salinity stratification that is different than the thermal stratification. Various physical mechanisms are involved. So then you end up with this isothermal layer and a isohaline layer, and the pycnocline, the isopycnal layer would be this way as well. So you have this so-called barrier layer. Essentially it's called a barrier layer because the wind-driven mixing then is not mixing colder waters, in this case a wind-generated entrainment and mixing would pick up colder waters into the surface and actually cool the surface mixed layer, whereas here you can have entrainment and you can still pick up temperatures of the same temperature and not have much of a cooling, and that's why it's considered a barrier to mixing. So it's kind of a decoupling of the dynamics of wind-driven mixing from the thermodynamics of entrainment, cooling, and so on. And then once the conditions become calm again, you can have surface heating, which can penetrate deeper and create this kind of stratification which then re-establishes the mixed layer. In this case, it's become shallower than where we started because of this freshwater forcing and the heat flux forcing. Okay, so this thing matters. Why? Because the inertia of the ocean is such that the imposed turbulent kinetic energy tends to penetrate into the mixed layer, and then to get deeper it needs energy to convert this colder, heavier water into the surface water. So that determines how deep the forcing can go, and that can determine the time scales of the response of the ocean to surface forcing. To run through quickly a few examples, this is the zonal wind in the at the surface measured at 165 east on the equator, Western Pacific, and 156 east, which is still in the Western Pacific. And you can see that the wind, the ocean response in the top 10 meters, this is the currents at 10 meters, do correspond closely to the forcing in the winds, even though you can already see that there is a low frequency rectification. So the ocean integrates the weather forcing from the atmosphere and creates lower frequencies. So you can see that here in terms of the higher frequency signal in the wind being converted into lower frequency both at 165 east and 156 east. The West Pacific is got a deeper mixed layer, and then the vertical structure of the current also becomes complicated. So you can see the eastward currents and the subsurface currents that are going the other way from the east, from the west to the east in the so-called equatorial undercurrent, and so on. So these complex vertical structures, surface jets, and remnants of previous forcing or currents related to large-scale tipping of the thermocline slopes. This is the temperature gradient. So the ocean response in currents to wind forcing begins to get multi-scale in time and space because of the ocean structure, ocean inertia, and so on. So the mean winds, trade winds, which blow typically from east to west, create a tilt in the thermocline from the Galapagos region to the New Guinea, Australia region, and we are just looking at the Western Pacific. So that's basically where I want to leave it, that the ocean creates lower frequencies from the higher frequency forcing in the atmosphere, and in fact some of the best theories of where the low frequency variabilities come from, like the classic paper by Hasselmann, relate to this ocean's ability to integrate weather forcing. The other things in the ocean are again related to the wave response that we will see in a minute. So here are the zonal winds over a few years, going from September of 1996 into March of 1998. Let me stop this here. So I'm going to stop this here because I have somebody coming into the apartment. I'll continue the ocean story in the next podcast. Okay.